should work.
It's an adventure every week with YouTube.
Well, especially because they've changed the way this functionality works, and now my method for being able to see the chat doesn't function properly anymore.
I
So.
swear
Alright,
they
we're
change
live.
they change it like every week.
Yeah, they do. Yeah, we're definitely live. Oh, and I forgot to mention, Alex, we take 5 minutes before we actually start the show. So we're live, but we're not actually doing the show. And
Cool.
and then giving people a chance to settle
Don't say
down.
anything you don't want the FBI to know.
That's right, yeah. So everything you say from this point forward is completely on the record.
All right.
Yeah.
Far out.
Man, people, this is so funny. People are like, are they late? We're 1 minute late.
Oh, they do not remember the old
They
days.
really don't. 1 minute late, and people wondering if things are off track.
man.
Is this what's going on with this rinky-dink operation?
It's like the wake-up call that we've actually gotten good.
Yeah, I know. How do you like this future that you're living in now, as opposed to the nightmare that we used to be in, where we would be 15 minutes late? Whatever. We'd start when we'd start.
Now that only happens when I'm in charge.
Yeah. Well, you whipped us all into shape, Morgan. It really was.
Well, yeah, but I'm unable to actually execute the program on time myself because I can never find all the buttons.
Yeah. Yeah, that's the terrible
When you only do it once every 3 months, it's like the whole interface is different.
Yeah.
Yeah, they're changing it all the time, aren't they?
They
YouTube
still
is the
are.
worst
Yeah.
tech company.
Yeah. It's a completely new interface now. It's better. It's way better. But it is definitely a completely new interface on what it was 2 months ago, and they're constantly changing it now. Like, for example, making key functionality just not function. So if I press the pop-out chat to be able to see the chat and put it in a little window that I can kind of move around.
That doesn't work anymore?
No, it doesn't work. Well, you click it and you just get this little box that's just empty and it doesn't do anything. So it's just a white empty box. Your chat disappears and you're left with a white box. It doesn't do
It's
anything.
your punishment box.
Yeah, exactly. Yeah. This is what you get.
This isn't the chat you're looking for.
I'm gonna say hi to. Oh, come on, pop-up chat. Nope, doesn't work. All right. So I'm going to say hi to a bunch of people. I'm going to say hi to Andy Cowley, Bob Harkins, Brexit Denier.
I got bad news.
I got bad news. I think it already happened. David Dunn, Ian Farquharon, John Victor, Johnny J, Johnny Zed, Kevin Ayers, Kevin N, Larry Beckham, Martin Bradshaw, Miguel Angel Romero, Miss Scooper, Nancy Graziano, Paranor, Pick and Duck, Rich Wilson, Arjone, Sergio Botero, and Zapfan. Hey, everybody. Welcome to the very regular Weekly Space Hangout. Actually, we got a special Weekly Space Hangout because we've got a new guest co-host, which is going to be great.
Hello, everyone.
You're gonna have to say that again in about 3 minutes.
It's all good.
Yeah,
Pretend
and then
like you're saying it for the very first time.
we've got a pre-recorded interview today with Professor Cole Miller. And we talked about mapping the surface of a pulsar and the neutron star interior composition explorer experiment. He was on the road in Brazil, so his audio wasn't fantastic, but the interview is absolutely fascinating, and we just get into just the nitty-gritty of neutron stars. So if you are fascinated by that topic, and just have faith in what is going to be a really compelling interview, stick around as we get into that part as well.
I want to go on the road in Brazil.
Yeah.
That sounds like a job I'd like to have.
Okay, well, we're at the 5 minute mark, so why don't I get this all organized again? There's us. There's me. Here's my intro. All right. Here we go. Hello and welcome to the Weekly Space Hangout for Wednesday, February 12th, 2020. I'm Fraser Kane, publisher of Universe Today. This week, we're going to be talking about the launch of Solar Orbiter, the new NASA budget, the White House NASA budget, let's be clear. There's a few problems with the Boeing Starliner, and SpaceX nabs a new executive from NASA, and Cheop's first flight. So we've got a lot of great stories. Joining me this week, we've got Morgan Renberg. Morgan.
Hey, Fraser.
Welcome back.
Thank you.
We missed you as always.
Yes, I miss it as always too, but life goes on.
And we've got a new guest host, Alex Tichy. Alex, welcome to the Weekly Space Hangout.
Thank you very much. I'm delighted to be here.
You have an awesome room behind you, by the way.
Oh yes, my office. Yeah, it's a pretty sweet
It's a
spot.
swanky office.
Yeah, I dig it.
So for people who don't know who you are, since this is the first time you've joined us, who are you and what do you do?
Yeah, my name's Alex. Once again, I'm a fifth-year graduate student, PhD student here at Columbia University in the Department of Astronomy. And my research here focuses on the search for exomoons. These are moons orbiting other planets, exoplanets, planets around other stars. At this point, we've discovered thousands of these exoplanets, but these moons are, as you can imagine, much more difficult to find, and there's very few of us working on it. So I've been very privileged to do this work with my advisor here, David Kipping, who's runs a Cool Worlds channel on YouTube. I'd recommend everybody checking it out. And yeah, it's a lot of fun. I love doing this work.
So you are still working on your PhD. You're in your final year of it, and
I'll defend this year.
And what will you end up having? Will you be like are you getting your doctorate in astronomy? Which
That's right. Yeah.
Yeah. Okay.
Mm-hmm. Yeah. PhD in astronomy here at Columbia, and then I'll be going on and doing a postdoctoral fellowship somewhere. Not ready to announce where I'll be going, but very shortly I'll have that nailed down. So starting in September, I'll be starting a new job and continuing doing this work. I'm very fortunate that I'll have the opportunity to continue to do this exomoon research, because I think it's very important. And like I say, there's very few of us working on it, so I'm anxious to see where we can keep going with this in the years to come.
So what is the state of exomoon research at this point? Now, I had heard, we reported a couple of times on an announcement that an exomoon had been discovered. Has an exomoon been discovered? Because I think it was later retracted. Where are we at in the state of exomoon discoveries?
So I would say that it has neither been discovered nor has it been retracted exactly. You could probably put an asterisk next to that one. That's actually my work with David for this system, Kepler 1625b. We did this Hubble observation back in October 2017, trying to confirm the presence of this moon, and spent about a year digging into that data. And our conclusion was that we did in fact see evidence for the moon, but it's certainly controversial. I would say there's people in the community, some people believe it, some people don't, and that's really all part of the process. We always kind of knew that being the first out there, and particularly with very challenging data to work with, that it's only natural that people are going to come along and kind of poke at the data and see if they can get the same result. And one team came along and did a totally independent analysis. They basically reproduced all of our findings. Another one came along and didn't get all the same results. And so from our point of view, it's still very much a candidate. Not everyone thinks so, but we're anxious to kind of see what we can do with additional observations.
But hasn't there been evidence that's turned up through, say, microlensing as sort of a different way to perhaps detect moons around planets as well?
That's right. So there was one paper several years ago that said maybe they thought they had seen a moon. It was actually, again, similarly murky. Microlensing is really awesome. If anybody in the audience is not familiar with it, what you're looking at is really, sort of gravitational warping of space-time. Microlensing, very small warping, but you can really see these planet mass objects by small changes in the light. That's really exciting because we are sensitive to these objects. On the other hand, it just you can only see this when an object is passing in front of a background star, and that's a one-way trip. So you see this thing happen one time, and then you never really get to follow up those observations. So I think microlensing is promising from a statistical standpoint. What can we say about the population when we see enough of these sort of events? But unfortunately, we won't be able to go after those systems later on and say, "Oh,
right, yeah, it's
really
a one-time thing.
We saw, yeah.
You see this flash, and then you can
exactly.
never study it again."
Yeah.
But
exactly right.
So then, which experiment or which upcoming mission? Because like at this point, with Kepler, which is no longer functional, with Hubble, which is busy. What is the instrument that's upcoming that you are sort of placing a lot of your hopes and dreams on, and being able to make these measurements with a lot more regularity and sort of certainty?
Right. So I don't want to, discount Kepler entirely. My work is still working with the Kepler data because there's so few of us doing this work. I think there's still a lot to squeeze out of Kepler. And then there's K2, which was the extended mission of Kepler, and then TESS. And so these data sets are really sitting there just sort of waiting to be explored. And so that's what my work will be doing in the near term. JWST, of course, this, most people think of it as a follow-on to HST. These telescopes like, HST, JWST are so much more sensitive that these are really going to be phenomenal if we can get the time. So we have to kind of convince people that we've got a convincing candidate in order to win those, time on those telescopes. We say it's oversubscribed. So many more people want to use the telescope than can possibly be awarded that time. And so that's why I think we've really got to focus on the data that we already have on hand, like Kepler, K2, and TESS. Got to squeeze what we can out of those data sets. And that's the way that we'll really be able to get that pristine data from JWST in the years to come.
Limp Rimple asks on Twitch, what type of cheese are exomoons made of? Have you guys put any thought into that yet?
Yeah, it's definitely Wensleydale.
Wensleydale.
That's Wallace and Gromit. He's his favorite. You ever see the grand day out? They go to the moon. He's slicing off the
right. Yeah, but I mean, really, you're going to need some kind of spectroscopy to really get to the bottom of it. So perhaps a suggestion on some new experiment to be added to one of these planet hunters. All right. Well, thank you so much for taking the time to join us today. You are, of course, this is half interview, half introduction, and half actual news coverage. So stick around, and you've got some stories to talk with us today. So, but allow me to speak for our audience and welcoming you to joining us here on the Weekly Space Hangout, and hopefully on a regular basis.
Thank you. I'm pumped to be here.
Right on. All right. So before we get on to the news roundup this week, I just want to give a big shout out and thank you to, of course, our good friends at the Weekly Space Hangout crew. These are the fans. These are the executive producers, the ones who bring in all of our guests, who organize everything behind the scenes. They have a great active community. You can see them chatting down below while you're watching the show, but they continue these conversations throughout the year, all the time. And so if you want to just hang out with other space people who really love this, go to wshcrew.space and they will hook you up. All right, Morgan, let's talk about Solar Orbiter.
All right, so I don't want to freak you out, but we don't know what the poles of the sun look like. We sort of assume that they look like the rest of the sun, covered in weird yellow sun stuff, but we don't actually know that. Because we've never seen the poles.
So there could be nothing up there. There could just be...
Yeah, it could just be empty. It could be, it could be like the top that the universe spins on. It could be coming out of the bottom of the sun. And we cannot prove otherwise until now. And
until of course, soon.
That's because the sun is big and the Earth is small. And Earth's orbit is so well aligned with the plane of the sun that with solar telescopes here on Earth, we can't see the top and the bottom of the sun. And all the sun-observing spacecraft we've sent in the past have also remained in the plane of the solar system because that's by far the most energetically easy way to move around. Going up and down is hard. Going in and out from the sun is a lot easier. And so we've studied the sun now for many decades without really knowing what the poles look like. And that's kind of crazy, because the thing we care about the most for the sun is the magnetic fields. And where do the magnetic fields come? They come out of the poles. And so, we obsess over the minutia of the sun's magnetic field and the solar wind and all of this without ever really having seen where it all gets going. And that's going to change in about 3.5 years. Because on Sunday, ESA launched Solar Observer on board an Atlas V rocket. And it's going to become the first spacecraft to orbit the sun and study the sun from an inclined orbit. So over the next 3.5 years, it's slowly going to step its orbit down closer and closer to the sun using gravity assists from Venus until it eventually gets just inside the orbit of Mercury. And then over the course of their mission, they'll be able to vary the inclination of the spacecraft from 0 degrees all the way up to 25 degrees. So it won't be like Juno, where they're going like right over the top of the sun, but it'll be high enough that they'll be able to look down on the poles and see what's actually going on. And they're going to be far enough away from the sun that they can actually take pictures and really see what's happening. So it's not like Parker's solar probe, which is so close to the sun that you can't use cameras. The sun just burns them out, and the field of view would be so small. 6 of the 10 instruments on Solar Orbiter are designed to take some form of image of the sun. And what I think is really cool is that NASA is a partner on this spacecraft, and the goal is to work together with Parker Solar Probe, which you might remember has been slowly inching its way closer and closer to the sun. And over the next few years, it's going to basically skim the surface of the sun. And so that means it's going to fly through the solar wind, through the outer layers of the sun, and measure what's actually going on in those areas. And Solar Observer is going to be able to take pictures of the whole region that Parker is in at the same time. And so we'll be able to see both the sort of minute what's happening on the kilometer by kilometer view, but also what's happening across the whole disk of the sun and what's happening at the poles. And this is all going to help us put together an understanding of the magnetic field of the sun that's going to help answer questions about why and how the solar wind gets going. Because then the solar wind is what affects the whole solar system almost more than the light of the sun does. And we really are only starting to understand like what's going on.
And I think this is like, I think a lot of people are quite surprised to hear that the Parker Solar Probe doesn't have cameras per se. As you said, it's getting like within 9 million kilometers of the surface of the sun, really close up, and it's a really extreme environment. While Solar Orbiter is still going to stay, you know, a little within the orbit of Mercury and just be able to get a really exquisite view of the surface of the sun from every angle, doing these, hopefully, you know, moving higher and higher to more and more polar orbits. It's a pretty exciting thing. Someone was mentioning in the chat, like, didn't Ulysses look at the poles? That was the European Space Agency's spacecraft that was back in the 90s. It didn't have a camera. So it smelled the poles, it listened to the poles, but it didn't look. And so again, you know, we don't know, but again, whether, you know, if those poles actually are the same sun stuff as the rest of the place.
Yeah, so this is all going to be really exciting, and they're already kind of thinking ahead to if the mission is successful and they're able to get an extended mission. The plan is to continue to increase the inclination of the spacecraft so that they can look more and more in detail on those polar regions. And so the whole mission is supposed to last about 7 years, and about half of that will be taken up by getting to the sun. And of course, they'll be able to make observations. They have solar wind measurement tools and particle detectors and magnetometers and whatnot on board. So as they're flying to the sun, we'll be getting all this great data in between. But the really sort of new important work will happen starting in late 2023, early 2024, when Parker will also be getting down to the deepest part of its orbit around the sun. So when it's really in there good is when we're going to be able to see both the big picture and the fine details at their best.
One of the things that really fascinated me about this mission was the method that they went into to actually coat the spacecraft. And so I don't know if you saw the story, but they ended up coating the whole spacecraft black. So, which seems bizarre. You'd think
it wasn't just any black either, was it?
Well, what they did was it's the same kind of they used a painting technique that is used for it's flat black, and it's a painting technique that's used for titanium medical implants. And so what they did was they actually sandblasted the pigment into the upper layer of the of the metal of the spacecraft, of the shield that it holds in front of itself while it's staring at the sun. It has these little windows that it peeps outside and then can shut these down as it's experiencing the most heat and temperature. And this technique ended up being so successful that they ended up painting 80% of the spacecraft with this technique. They just started painting everything they could to maintain a constant temperature profile for the spacecraft.
Yeah, what I thought was so cool, though, was what that pigment actually was. It's crushed up, charred animal bone. It's the same, literally the same stuff that was used to make the cave paintings at places like Lascaux. But it happens that when you char the bones, the chemical properties that you get from that pigment are like perfect for shielding a spacecraft from the sun. And so there's just this like amazing symmetry between like the first scientists 30 or 40,000 years ago and cutting edge space technology today. And it's like never went out of style.
Alex, what do you think about like the level of observations that we're now getting with the sun, with Parker Solar Probe, with Solar Orbiter, with the Daniel K. Inouye Solar Telescope, for us starting to think about these other stars and maybe the planets orbiting around them?
Yeah, the sun is very important. I think it sort of amazes a lot of people when we talk about all the things that we don't know still about our own sun. And, it's the only star that we can see up close. And so we can see incredible detail on it. And so much of our understanding of astrophysics is still kind of tied to this single data point. And it's, I think, very much an open question about how similar or how dissimilar other stars are. Of course, there's a range of masses, a range of temperatures of stars. And so we know that, for example, red stars are much more active than the sun and all of these sorts of things. But it is an extremely important laboratory for understanding things like star spots. Star spots, incidentally, affect us. It comes up all the time about the exomoon question. Are you just seeing star spots? This is very challenging to say from far away. So every time that we can understand more about our sun, it's obviously important for us because it powers us. We have these solar storms. There's all kinds of immediate environmental impacts that the sun has on us. But from an astrophysical perspective, it's definitely very important as well.
Yeah. Very cool. Well, here's for a successful orbit. I mean, at this point now, everything's nominal. And so hopefully the mission will continue on and we will get this sort of triple look at the sun from these different perspectives, plus all the other spacecraft that are observing right now. All right. So Alex, why don't you bring us up to speed on the White House budget for NASA?
Sure. Yeah. So the White House, of course, every year they put out their own budget. This is the sort of first stage in budgetary negotiations, right? The White House proposes this is what we're going to spend, and then it goes off to Congress, and Congress says yes or no, and they push back and all of these sorts of things. So this just came out, and we were joking around before the show about how this is just kind of every year we have to talk about this, and I think anybody who's not observed this over the years thinks that, oh no, the White House is cutting this and is cutting that. All of our favorite projects, they're going out the door. Spoiler alert is that Congress almost routinely restores all of these things back to the budget. So they never actually go away. But just to kind of quickly give you a rundown of what the White House is proposing to cut. I think the biggest one is WFIRST. This is sort of the next flagship mission. That's the Wide Field Infrared survey telescope, I believe. The missions there are to probe dark energy, as well as I think they want to do some exoplanet microlensing. So, I'm interested in, and a lot of this was sort of a top priority in the decadal survey.
Yeah. And, I think one thing that I think people are always so nervous about James Webb and all, how it's 10 years late and however many $1 billion over budget. WFIRST so far has been perfectly on time, perfectly on budget. It is a textbook example of how to do a mission right, and it's based on Hubble architecture. So, it's lessons were learned, right?
Sure, yeah, and I think if you read the the White House's sort of explanation, or the administration's explanation of this. They say, JWST, because of these budget overruns, they're sort of shoving W first out. There's just kind of not room for both of these things. So that's the first thing that's out the door. The other thing is, from an astrophysical perspective, is Sophia.
Oh.
This is this really awesome 747 with a telescope hanging off the side, or the door opens, they fly at 41,000 feet, and they have an infrared telescope. This is amazing because they can get above most of the water vapor, and so they can probe really deep into the infrared, something that you just can't really do from the ground. And this is, I think, a lot of astronomers have a special place in their heart for Sophia. Sophia is one of these missions that every single year it seems like it's up on the chopping block, and of course it's still with us. So I don't think there's anything really to worry about for W first. Sophia, might be a little more risky, but I think it's probably going to stay with us. But it costs, as you can imagine, quite a bit of money to operate this telescope. And it's all targeted observations, right? There's no, W first at least is a sort of a survey mission where the data comes down and everybody can use it. And Sophia, not so much. There's also a couple of Earth observing spacecraft that have been proposed for elimination. There's a spacecraft called Pices that stands for Plankton Aerosol Cloud Ocean Ecosystem. And what this does really is sort of monitor the color of the ocean, basically, and looking at phytoplankton, these algae blooms,
Wow.
and trying to kind of monitor the health of the oceans and bodies of water. And then another one called Clario, Climate Absolute Radiance and Refractivity Observatory. This was sort of interesting. I was digging into it. This mission has had a long history. They originally wanted 4 orbiters for this mission, but it got cut back way back in 2012, and they turned it into what's called a Pathfinder, right? Where they say, okay, well, this will be kind of a proof of concept mission that we do it on the cheap, and then if it works, then we'll kind of follow on with another mission that goes much farther. And then now in this new justification, they say, well, it's a Pathfinder, but it's not clear that we're ever going to, make the thing. So what's the point of having a Pathfinder if we're not going to follow on this technology? So I was getting really deep into the weeds of this. It turns out, even before this budget came out, there's already a bill in Congress, HR 5666, sponsored by Congresswoman Kendra Horn from Oklahoma's 5th congressional district, and this, as you might imagine, reinserts all the funding for all of these missions that have been canceled, and funding for these sort of things is always interesting because it doesn't necessarily cut along partisan lines the way we expect so much in Washington to do.
This is the biggest NASA budget in decades. If we're cutting these things, where's all the money going?
I wonder.
Yeah, it seems like it's going to crewed space flight. That's always, that just gets so much fanfare. People love crewed space flight. So going back to the moon and Mars eventually, they're still holding strong with this 2024 deadline to return humans to the moon. I think most observers are skeptical, if not deeply skeptical, of that timeline, at least with this funding profile that they've got going on. But they're that's really where they're socking a lot of their money. In fact, the Planetary Society has a fabulous website that very cleanly breaks down the fiscal year budget and shows you percentage for each little thing. What's getting cut. They've also cut about $1 billion from SLS Block 1B. This is sort of to extend the heavy lift capabilities of SLS. I think they want to see SLS work first before they start thinking about the kind of stage 2 of the SLS.
And that is actually pretty important, because some of the future components of the Lunar Gateway is going to depend on this heavier lift. Plus, there's other ideas like the Europa Clipper, and even sending, say, the more capable, like a lunar lander. They've got some plans that you can send sort of separate pieces. So you could send like the lunar lander, a transfer module, and an ascent module all to the to the lunar gateway, and then they can be as 3 separate launches on, say, Falcon Heavies, and they can be combined together and then go down to the surface of the moon and then come back. But to sort of simplify the process, if you just want to do one launch, you stack it all up on one of these 1Bs, and then you're able to essentially do your entire lunar architecture in one launch. And so there are theoretically some, I mean, I guess nothing is a cost savings over an SLS, or everything is a cost saving over an SLS. But still, there is some ideas, some reasons why they would want to kind of go heavier after what they do. I mean, if they are serious about getting back to the moon, they're going to need these heavier launchers. And
seems to be a lot of emphasis on going in the commercial the commercial. I always want to say commercial crew, but commercial heavy lift seems like it's looking very promising, and so any way that they can save money, they're always wanting to do that, and so they definitely want to diversify and not put all their eggs, I think, in the SLS basket.
What about a lot of the the educational programs that always seems to get on the chopping block? All of this outreach and education that we depend on so much for what we do. Right. I'm sure that's all in the gun sights.
Yeah. Again. So the Office of STEM Engagement is what has gotten the axe. This is $120 million per year, and I think I was trying to dig in a little bit, and people were sort of tweeting that they had gone to school on these sort of NASA graduate research grants that, as far as I can tell, are offered through Office of STEM Engagement. Now, I think we sort of almost sometimes we have a knee-jerk reaction. If you're going to cancel, say, a climate spacecraft, it's very natural to say, "Oh, they're going after climate science." And the reality is that sometimes things do really get cut. So it's not obvious to me that they are not trying to clean things up a little bit. And there's always sort of mission creep in any sort of agency, and so if they're reorganizing and kind of moving these scholarships to different places, that is all totally opaque. I mean, I think you have to dig really into the weeds. So the short answer is that this office is getting axed, and people are necessarily a little concerned about it. And hopefully these programs don't go away entirely, but that they kind of get housed elsewhere or that kind of thing.
So what do you think, Morgan?
It remains to be seen.
How much of this remains like previous years? Like I've almost got to the point now where I just kind of ignore this White House proposal because everything just gets rolled back. What do you think, Morgan?
Yeah, well, the president's budget is never worth the paper it's printed on. What you should, in terms of like actually
it's just
enacting
like that's
things
not a specific
law.
Political thing. All president budgets.
Yes, regardless of the administration, the president's budget is like a fairy tale wish list. But that fairy tale wish list is important for a couple of reasons. For one, if the government gets shut down, then during continuing resolutions, some provisions of the president's budget will take effect by default. But more importantly, NASA is an executive branch agency. And so what NASA's budget, as proposed by the president, tells us is basically what NASA's priorities will be. There's only so many things in a given year that Congress will require an agency like NASA to do. For everything else, it's up to the agency itself to kind of say, okay, I've got this big pot of money. I want to divert it in these ways. And the president's budget is a really valuable insight into understanding when at the margins it comes down to, should we spend money on X or Y? Which way are they likely to make that decision? Because NASA doesn't have to provide like a written plan for what they're going to do for the year. This is basically that. And so what we can see here is that NASA's priority is human space flight. And actually, for the first time, the president is suggesting NASA gets provided resources basically to make that happen.
Right.
This is a big increase in NASA's budget of billions of dollars that is devoted basically entirely to human spaceflight. And in some sense, regardless of whether you think human spaceflight is a good idea or not, that's a good thing. Mm-hmm. Because if NASA's going to do something, they ought to just do it. And going halfway into human spaceflight, and talk this story to death
Yeah.
year after year. Going halfway into human spaceflight is the worst of all worlds.
Yes.
And that's where we've been for years. And so to say we're going to cut these other things in order to get this one thing done in the next decade is a good thing from a certain point of view, regardless of whether you'd rather have 50W firsts instead of, you know, any Artemis missions.
And I think that, you know, this idea of it being like it has to be this or that, right? That W first is in space and astronauts go in space. Therefore, you have to decide whether you're going to have one or the other, right? But I mean, buildings are built on the ground and cars drive on the ground. Therefore, you know, but you know, people decide on buildings and people decide on cars. So and space is really big. So there's a lot of room out there to have all kinds of different things happening out in space. And so I think it really is a fault. I mean, NASA just happens to be the agency that helps figure out the transportation and organize the activities outside in space because the domain is different. But at the end of the day, you know, what do you want to accomplish in these different areas? The other thing that kind of dropped is a pretty big jump in the budget for Space Force. They're looking for many billions of dollars more than the amount of funding that was assigned to the Air Force and various agencies as part of its work in space. And so it may very well be that we're going to see some of these activities that were maybe done jointly through, you know, handled by NASA could end up in, you know, some of this work could end up in the hands of Space Force, which is just ridiculous to just say Space Force. I understand. It's such a weird thing. All right, well, we're going to run out of time if we don't keep rolling. So, Morgan, let's just talk a bit about what happened with Starliner. Uh-oh. In the words of a certain podcast or a certain YouTuber, they had an oopsie.
Yeah, not great. It came out about this time last week that in the aftermath of Starliner's aborted demonstration mission, that there actually were two errors, not the one that we all knew. So we all knew the one with the timing controller and the thrusters firing at the wrong time and all of that. And that's what caused them to expend too much fuel and have to abort the mission early. Well, we found out about a week ago that right before, and I mean like an hour before they returned the spacecraft to orbit, they uploaded like an emergency software fix. And the way, and this is all being described sort of by, you know, anonymous sources through unnamed channels, but the way they described it is that if they had not added this software patch, the spacecraft would not have survived re-entry. And there's some speculation about whether this could be another thruster problem related to the same timing issue, or whether it's a totally separate problem. But, you know, the spacecraft would not have survived re-entry is not what you want to hear on what's supposed to be the mission before you put people inside your spaceship.
Yeah, and what you do is you say, hey, we found a software bug that might mean that this spacecraft will not survive re-entry. We should scrub the launch, not, you know, hurry up and get and upload the patch. You know, you could just see the progress bar going up while the rocket is, you know, the timing is counting down. You know, come on, upload.
Yeah. So I think it's fair to say that NASA is none too pleased about this revelation, and Boeing is going to have to undergo a much more rigorous evaluation of their safety culture. And this is a problem they're confronting at all divisions right now. But I think it's likely that we're going to see NASA require Boeing to fly a second demonstration mission uncrewed before trying anything else.
Yeah.
And that's going to put them, you know, we don't know how deep these software problems go. They're, you know, many months, if not years away from actually putting crew into orbit. And that seems extra bad since NASA has also said that the Crew Dragon is ready to send crew to orbit as early as late March or late April.
Yeah.
And so it seems, barring some unforeseen catastrophe for SpaceX, that they're very likely to win that race for the first commercial crew launch. And
possibly even have like a year head start. It definitely makes choosing both Boeing and SpaceX as companies to develop crewed missions a wise move. Like in retrospect, it's clearly, having this level of competition clearly, I think, was a smart move. So whoever
Yeah, and do you know
chose
who
that,
the guy was that decided there should be a competition for this
you've
launch
been set up.
services?
So hit us with
Yeah,
it.
yeah. So that was NASA's associate administrator for human spaceflight, Bill Gerstenmaier, who for the better part of 15 years led NASA's human spaceflight programs from the space shuttle to the space station to commercial crew to early developments on Artemis. He was an engineer that worked on the development of the space shuttle decades ago, and I think it's fair to say is among the most respected people in the world for aerospace safety and aerospace technology. And he was demoted last year in the summer by NASA Administrator Jim Bridenstine because they felt like if they were going to hit these rapid deadlines for Artemis, that they were going to need to progress more quickly than the safety first culture that Gerstenmaier really focused on was going to allow. And we found out just today that Gerstenmaier has left NASA and taken a position at SpaceX, where he's going to help oversee the safety culture and mission assurance at SpaceX. And it's hard to overstate what a big
Yeah.
get this is. I mean, the guy who runs space program for Russia, who spends his days bashing everything touching American spaceflight, sent out his congratulations to Gerstenmaier and SpaceX on this development. And he's going to unlock every door in the industry for SpaceX, and has this proven track record of getting things done in a way that's safe and technically grounded and listening to engineers and doing it right.
And I mean, you can see how this is going to work. Like, either it's going to be a revolution at SpaceX. He's going to bring a level of sort of safety mindedness and quality assurance, et cetera, to the environment, or he's going to leave in disgust in about 5 months, having to work with Elon Musk, who is all about flying by the seat of your pants. Much to his credit, things are getting done, but at the same time, it is going to be a pretty rough road, I think, for the two of them to work together. But who knows?
Yeah, and I think one of the biggest dividends for SpaceX here could be if Gerstenmaier stays around. That's a sign to NASA engineers that, hey, it's not a bad idea to jump ship.
Yes.
And sign on here. And as Starship ramps up and is the most exciting thing in space technology and engineering right now, you might wonder, hey, is this really a thing that I want to be involved with? And if he's there and has influence and sticks around, then that's like a flashing neon sign to come here.
Yes.
Because things are being done right, and things are being done presumably quickly.
Yep.
And we'll know in the next year if that's true, and it'll give us a huge barometer on whether Starship's going to be a successful program or not.
And I guarantee, right, it's those two things. I mean, I think you hit the nail right on the head, right, which is that it's being done right, and it's being done quickly with respect to the ideas of the engineers, which, Elon Musk is an engineeringly minded person, and the whole company is driven from that engineer mindset. And at the same time, the employees are going to want to make sure that that lives are going to be protected, that there is a level of safety. They don't want to be held, they don't want to be responsible for people losing their lives on these vehicles that they're creating, that we're going to be depending upon. So I think you're absolutely right. It is the perfect combination if these two personalities can work together to thread that needle. I think it'll be I think you're exactly right. It's just going to be this beacon that just says, good times over here. Like, why suffer?
We'll find out in the next year.
We're running late, but Alex, I'm going to give you like 2 minutes to talk about Cheops, because it's pretty cool, and I think we need to explain the image.
Sure. Yeah. So Cheops, this is this new space telescope. I didn't mention it before when I was talking about all the other space telescopes, but Cheops is this brand new instrument coming out of ESA. They launched it back in December. And they just had in the last day or two what we call first light, the first time that the telescope really, gets on the sky and takes an image. And that's really the first time that, of course, they've done a lot of tests in the laboratory, but the first time that it's really flying. How did it survive the launch, and what is it? How is the optics looking? It's very important. And so this is the first light image, and it looks kind of
it's out of focus.
Maybe, yeah, it's out of focus. They do that intentionally. It stabilizes the image that you can kind of you can do better if you're not concentrating all the light on a few pixels. That can kind of what happens is that it can kind of saturate. They're particularly interested in with this mission to go after bright stars, nearby stars and bright stars, and they're trying to find these, super Earths and mini Neptunes, and so they like I say, they defocus the light intentionally to kind of get more stability in the data.
Yeah.
So how's this different from TESS?
So TESS is a survey mission, right? That it's scanning the entire sky, and it has scanned at this point the entire sky.
So this is looking at one star at a time, basically.
Yeah, and so about 80% of this mission is they've already sort of designated these targets. Some of them are planets that they already know, that they're it's almost kind of like a pathfinder for JWST, that they really think that these planets are sort of the most ripe for characterization. So they really want to nail down the sizes of these planets. It's still a transiting mission, so they're going to see the sizes of these planets, get really good precision on those. They also want to go after these planets that are known right now only through radial velocities, and so they want to see the transits and again kind of zero in on the densities of these planets. And once you have the mass and once you have the radius, then you can start to say something about the composition of these planets.
Right on. So I think this is the best we're going to be able to really hope for as looking at photographs taken by Cheops, but hopefully the data. I mean, what's key is that you've got this, the spectroscopy, you've got the detecting the changes in light, and hopefully we're going to find a ton more about potentially hundreds, if not thousands, of exoplanets. So it's a great spacecraft. All right,
exciting times.
We've reached the end of the main part of the show. Like I said, we've got an interview we got to run, and we're going to run late. I apologize to everybody, but we had to sort of give Alex his trial by fire, which was to cover the budget. So you did a great job. So if people want to follow more about what you're doing, where can they go?
Sorry, about me.
Yeah, you. Where people want to follow you. Yeah, right. They want to follow your personal journey.
Follow me on Twitter. He says it's a whole grab bag of stuff going on over there. But my handle is just my name, Alex Tichy.
Okay.
Teachey. Alex Tichy. And follow me over there and engage.
And then what's a project that you're working on right now that people should be aware of?
Trying to bring this dissertation in for a landing. What I'm doing now is really exciting machine learning to go through the Kepler data and looking at something like 1.2 million transit events and seeing which of those events have these tiny little signals that we think are maybe moon signals, moon transits. And so we're going to once we identify, it's a huge amount of data to go through. Once we identify some interesting targets, then we'll go and do a deeper dive on those systems. So it's been pretty awesome. I think it's working out pretty well so far.
Awesome. Well, again, thank you so much for joining us today. You did a great job. You will be invited back. Can't wait to have you rejoin us. Morgan, where can people find out more, and what are you working on?
Yeah, the website's morganrenberg.com, and you've got just over a month if you want to check out my awesome exhibit on the Apollo moon landings. We're closing on March 22nd. So if you're in the Midwest, drive on down to the Fort Worth Museum of Science and History, and you'll have a blast. And then a month later, we're going to be opening our brand new exhibit called Project Planet, all about climate change and what we can do to stop it. So that's been eating my life for a year, and I am excited for it to burst free into the world and to see what happens.
Well, it's a noble cause. That sounds great. All right, and of course, we've got lots of videos on my channel. I just did a video about the solar orbiter, which is why I kind of knew a little bit about it this week. On Friday, our next episode is all about the weight calculation, which is this idea of, does it make sense to send a spacecraft to Alpha Centauri, or should you wait for better technology? And what is the ideal time to do that? So that is the video that we've got releasing on Friday. And then on Monday, I cover all the Artemis lander options. So stay tuned for that episode as well. All right, so I'm going to say goodbye to my co-hosts, and then but everybody needs to stick around. Here we all here now, but everybody needs to stick around because now I'm going to play the interview, and that's going to run for about 20 more minutes. So again, I apologize for going a little long, but it seemed like a very special event. Need to make sure Alex felt comfortable and properly roasted. So now we can shift the episode. So thanks, Morgan. Thanks, Alex, and thanks everyone for watching. And the usual moderators, all the friends at the Weekly Space Hangout crew. Really appreciate you all joining us this week. So again, stick around. This interview is fantastic. But for Alex and Morgan, they can say goodbye now.
See you next time.
Happy trails.
All right, so let's get on to the main interview. Again, this is about 20 minutes long, so stick around. And like I said, it's a fascinating interview with the person who's working on this. And let me see if I can make this go. Let's see. There we go. All right, here we go. It's me, but I'm not talking. Miller from the University of Maryland. Cole, welcome to the Weekly Space Hangout.
Thanks, Fraser. Appreciate it.
So where are you located right now?
At the moment, I'm actually in Brazil with a colleague, but I'm going to be back in Maryland soon and then off to the Netherlands. And we travel a lot in this business.
At least you don't have to go to space to do your work.
No, one advantage of being a theorist is I can sit back and wonder about things. But it is also useful to work with people who know what the universe is actually like because they observe it, whether ground-based detectors or in space.
So normally I ask this question, who are you and what do you do?
Well, as you said, I'm Cole Miller, and I'm a professor of astronomy at the University of Maryland. What I tend to work on are extreme physics in astronomy: black holes, neutron stars, gravitational waves. And really, it's the realization of a dream I've had since I was a very young kid, because how often do you get to essentially do things that are almost science fiction, but for a living?
And I know that your work fairly recently was to really help understand and categorize neutron stars.
Exactly, yeah. Neutron stars are those extremes. They're remarkable objects. They pack more than the mass of the sun into an area that would fit inside of a city. And their properties, their strong magnetic fields, the nature of their matter, their centers, is a real mystery. And therefore, by studying them, we can learn more things about extreme physics. And one of the persistent mysteries that we'd like to get at from astronomy is, how big are neutron stars? What is their diameter to a certain precision? Because it turns out that if we can figure that out with reliability, the physics of their interiors.
Yeah, we did get to warn everybody, we've got a bit of an intermittent connection, so if it's a bit of a problem, I'll try to edit this down, but we'll see what happens. Yeah, and so, I mean, you say that the size of a neutron star fits within a city, but now you know the answer a little more precisely than that.
Yes, exactly. This was one of the main goals of the NASA's mission, the Neutron Star Interior Composition Explorer, or NICER. So NICER is something that flew up to the space station in June of 2017. And its goal to measure the size of a neutron star, well, a little background might help. How do you measure the size of something in astronomy? It's not as easy as you might hope to begin with, because even though these objects say something the size of a city, they're so far away that they look like points. So you can't just say, well, I know it's this distance, I know it's this angle, so it's got to be a certain size. People have been trying for a long time to figure out their sizes, and if the approach they're using is correct, then they can get the sizes, but unfortunately there are a lot of ways we can be completely misled. But the method that we're using with NICER is one that, based on previous studies, we think is going to avoid that kind of unreliability so that we can be not just precise, but also reliable. And the answer, as it turns out, from the particular neutron star we examined, is that the radius is something like 13 kilometers plus or minus 1 kilometer. And that's already enough to give us much better hints about the nature of the dense matter in their cores.
All right, so you're going to have to go into more details then in the technique to actually figure it out with that level of precision. I mean, astronomers still argue, or were arguing over, say, the size of Pluto, which is in our own solar system. And it wasn't until New Horizons did its flyby and it could actually measure it up close that we got to get a much more accurate idea. And so, you know, if we're still arguing about the size of objects here in the solar system, it's incredible that you can determine the size of an object that is hundreds of light years away.
It is pretty amazing, I have to admit, that the scales in astronomy are one of the things that has really attracted me to the subject. So to answer your question, you can ask yourself, how would you be able to determine the size of, let's say, another star? That's not so easy either. And you work at it, and some things you could imagine is that if you look at the star and you treat it like a black body, so something that's just a hot object radiating normally, and you know how far away it is, then by how much light we're getting from it and the temperature of the object, you would be able to get the size pretty well. And you can check this out by knowing the actual size of the sun and the size of Betelgeuse and a few other stars where you have different methods. The difficulty is that if you try that with a neutron star, which has been a standard method, at least initially you get ridiculous answers where the size is 2 kilometers or 4 kilometers or something. So actually it's way smaller than a neutron star could be. The method that we're using is if you have a neutron star which has a hot spot on it, so you can think of something attached to the star rotating with it a few hundred times a second. This hot spot is emitting X-rays. It's emitting X-rays in a way that we kind of understand. And by looking carefully at, as a function of how it's rotating, the spectrum, the X-ray spectrum of this, we're able to do analyses that bring in extra information, and work that we've done with a number of people suggests that this is going to give us a reliable answer. And what I mean by that is the following. Suppose you have an idea, okay, this is what the neutron star is like. Here's a model I have to describe the neutron star. You can see whether your model fits the data well in a statistical sense. Previous methods, the problem is you could have a good fit, but be horribly wrong, getting an answer of 2 kilometers when the answer has to be somewhere between 10 and 15, as it turns out. But the method we're using with NICER, if you get a good fit, you're not being misled. And this is something that's been won by a lot of simulations, a lot of discussion in that sense. So this is why we refer to this as the first reliable set of results, as well as being precise.
I'm kind of imagining an analogy of like watching the sun and watching as sunspots pass in front of the sun, and you can see when the sunspot first appears on one limb, watch it as it passes across, and then watch as it disappears over the other side, and then use that to try to calculate the size of the sun. But I mean, neutron stars, like the extremes involved. So how do you detect a hot spot on a neutron star? And how do they even get hot spots?
Both are excellent questions. And at first, let me go back to your excellent analogy with respect to the sun. Let's suppose you knew that a sunspot was at the equator of the sun. And let's suppose you knew how long it takes for that sunspot to go around. Given that, you know how fast the sunspot has to go, but only if you know the size of the sun. So if there's a way that you can figure out how fast it's moving in kilometers per second, and you know how long it takes to go around, that's a way of measuring the size of the sun. In the case of a neutron star, to answer the question about how you get these are pulsars. So these are things that emit radio waves. And the way that this happens, they have very strong magnetic fields, and charged particles are being accelerated along those magnetic fields to within a tiny fraction of the speed of light. So they're really, really moving fast. When they slam into the other side, then they release energy, and that energy gives us the X-rays that we see. So essentially what we've got are, because you're tending to focus these very fast charged particles along the magnetic field lines, they're kind of hitting in spots, like the magnetic poles. In fact, very much like the aurorae on the Earth. And so that is giving us these X-ray hotspots, and they're rotating with the star. So we know the rotation rate in hertz, say, times per second. And if we magically had the knowledge of their being on the equator and we're looking in the equator and so on, then it'd be a fairly straightforward thing to figure out the size. But of course, we're not that lucky. There are lots of uncertainties. But what you do is a fit with more parameters. What are the angles? Where are the spots? Where are we relative to the rotation axis and so on? You do a huge fit of all this stuff, and you come out with the information you really prize, the radius, but also the mass of the neutron star. So that's the essence of the method. And as I say, the advantage of working prior to this with synthetic data that we've generated, where we know the real answer to how big this synthetic star is that we're able to check to see whether even mistakes in our model could give us misleading answers that nonetheless appear to fit well. And that has not happened. And so this is why we're fairly confident in the final answers.
Well, and you mentioned that you're getting, I mean, the rotation rate is one thing pulsars can tell us. It's how quickly they're rotating. But you mentioned that you have a way to be able to get at the mass, and that's actually a very tricky thing to do in astronomy. So how are you finding out the mass?
Exactly. And this also comes down to the precise nature of the X-ray spectrum as a function of the rotational phase in the following sense. You may know that gravity deflects light. There was a famous experiment and observation that Arthur Eddington was involved with in 1919 to help confirm Einstein's general theory of relativity. Well, the sun deflects light, but not very much, about 2 seconds of arc max. Neutron stars are a lot stronger gravity, so they're able to bend the light much more. The reason this is relevant is if you think about observing, say, the Earth from a really large distance, you can picture this and you will see half of the Earth at one time. But for a neutron star, because light is deflected, you could actually see light bending from around behind the star. You can actually see, therefore, more than half of the star. And this means that if you have a spot, even if it's on the equator, you can see it for more than half of a rotational period. Now that's relevant because what really determines the amount of bending of light is the ratio between the mass and the radius. So by seeing how much light has been bent and knowing the radius, you can get the mass. You get them both for the price of one, which is, as you say, not an easy thing to do, especially because the results we published in December are for a neutron star that is isolated. It has no companion. The traditional way of measuring mass is seeing things orbit around the thing you care about. But even without such a thing, because of the nature of the bending of light, we are able to figure out the mass as well as the radius.
So, people always say, like, why don't they put a telescope on the International Space Station? And I always respond that they have. It's just in X-rays with the nicer instrument. Can you tell me sort of what are the capabilities of this instrument? How far away will you be able to probe with nicer to be able to maybe find other objects out there in the universe?
The answer is that the limitation is actually the flux of X-rays that we're getting from an object, meaning that if we had something that was unbelievably bright and was in the Andromeda Galaxy, hey, we're happy to work with that. But as it happens, the neutron stars of interest are ones that are dim by neutron star standards. Mind you still wouldn't want to stand next to one. But these are a few hundred parsecs away. So the one that we studied in particular is about 1,000 light years away. There are others that we're also examining, and we're going to be working on them, trying to make sure that we understand the systematics, meaning the things that might not quite seem to work well enough. These are very important to understand. And we're hoping within perhaps this year to be able to have 1 or 2 more neutron stars where we're able to report the results of our analysis.
And so do you think that you're going to find a lot of variation? I mean, you mentioned 14.1 kilometers. Do you think that you're going to be finding a lot of just difference in size between neutron stars, or is this like almost like a Chandrasekhar limit? Like there's a precise size these things end up at?
Right. So the 13 plus or minus 1 kilometers that we
Yeah.
got for this one is something that I think that we would expect for all neutron stars of the same mass. And this is important to understand because one of the many bizarre aspects of neutron stars and some other things in astronomy, when you think about a heavier thing, you tend to think about a bigger thing. Jupiter's heavier than the Earth, Jupiter's bigger than the Earth. But it turns out that for objects like neutron stars and also white dwarfs, it doesn't necessarily work that way. Detailed analyses, specific theories suggest that for neutron stars, you have a fairly similar radius over a relatively wide amount of mass until you get to the maximum mass that a neutron star can have, which is not well known. And then it actually starts to decrease in radius with increasing mass. But this is one of the key things we want to find out. Another thing to point out is that because of the nature of neutron stars, it would be expected that all neutron stars of the same mass would be basically the same size. And if you think about that, this is not an obvious statement. You think about stuff on Earth, for example. So suppose you have 100 kilograms. Well, 100 kilograms of water and 100 kilograms of air have very different sizes. But when it comes to neutron stars, the thought is that there's an equilibrium state, so that it's going to be in a fairly well-determined state. Not that we know it well, but that it'd be a well-determined state. So this means that something of the same mass should have at least a compatible radius. Something of significantly higher mass would be interesting because it could be significantly smaller in size or comparable in size. And therefore, the more we can study, the more different neutron stars, the greater leverage that we have on the properties of this matter.
And it feels like the more that you can find, eventually you will find the most mass. Because you have such a great way of finding mass, you will find the most massive neutron star, and that will probably tell you the defining limit between neutron stars and whatever comes next, right, as they turn into black holes.
It's an interesting question. Right now, the best way of determining neutron star masses is actually by radio wave observations of neutron stars that are in binaries with other stars, which makes the mass a lot easier to figure out. And there have been some pretty massive ones found. There's one that's a little more than 2.1 times the mass of the sun, whereas the one we studied turned out to be about 1.4 times the mass of the sun. But here's one of the funny things about astrophysics. Yes, it's true that if there is equal opportunity to get to any mass, then the highest mass neutron star you measure is probably very close to the highest possible mass for a neutron star. But neutron stars go through odd formation channels. They come from the death and collapse of massive stars. And it's very possible that in many circumstances, you just form something that's much less than the maximum mass. So we don't know, actually. If we find a limit, it could be because that's the absolute maximum that you can do. That if you were to apply your godlike powers and pour matter on a neutron star, you would just collapse black hole. The processes that form and allow neutron stars to evolve simply don't get to that maximum. It's an interesting question that collectively we have to pursue.
And I mean, as you said, you could pour mass on. I mean, you can have a situation where a neutron star is feeding actively off of some companion star, like we see with white dwarfs. Do you think that there is some kind of intermediate stage if you have that kind of a process between a neutron star and a black hole, or is it just straight to black hole?
This is something the community is discussing. Because in the same way that, suppose you take a white dwarf, as you mentioned, and you pour mass onto it. And if you've made that white dwarf out of heavy enough stuff, so things like silicon maybe, you pour enough mass on it and it'll collapse, but it'll stop at the neutron star stage. What happens to the neutron star? If you pour mass on the neutron star, will it collapse a bit, but then halt at a quark star stage or something? We don't know. There's disagreement. Some physicists believe that, in fact, it will collapse all the way to a black hole once it starts collapsing. Others think there's going to be an additional family of compact objects. The work that we're doing and that people are doing using gravitational waves, which is another way to get at the properties of neutron stars, this is going to provide information, but maybe not the immediate info of that. It'll simply provide clues so that physicists are able to put together a more complete picture.
Absolutely fascinating. Professor Miller, if people want to follow what you're working on, where can they go?
You can certainly go to the NASA NICER website. You could go to my personal webpage at the University of Maryland. There are a variety of spots, but I think that there are so many interesting avenues to follow the progress of astronomy, including your show, of course, that people have the opportunity to participate vicariously in the discoveries about the universe.
Well, I can't wait for more discoveries and you getting an even more precise measurement in the future. So thank you very much for taking the time to chat with us today.
Thank you, Fraser.